So let's continue with the last talk of the day. As already announced, Martha is also works on a lot of these relational and compositional structures. Martha is assistant professor of neurosymbolic AI at the Institute of Logic, Language and Communication here in Amsterdam. But she previously held academic positions at the universities of Oxford, Bristol, and Sussex.
Sussex was just a master's.
Okay, that's an academic position. Yeah. Among many things, she studies the compositional structure of language and concept. That is, what happens when you put words or concepts together. And she developed methods to quantify the intelligence of AI, and recently worked with Melanie on quantifying the robustness of analogical reasoning. And today she will tell us about an important difference between behavior and representation.
Okay, thank you very much. And thank you very much for inviting me to give the talk today. I've really enjoyed all the talks so far. And I hope I don't keep you too long from the drinks that are following this. Okay, so yeah, I'm going to talk about behavioural versus representational systematicity in artificial intelligence. Okay, so as humans, we're very good at systematic recombination, okay? So if I give you this little puzzle, okay, there's some coloured shapes, and there are some labels for these coloured shapes, and your task is to work out what label this coloured shape should have. What do people think?
Nada.
Nada. Yes, I can't even remember which way around it is, but yes, it is. It's nada. Okay, and at least a few months ago, large language models were not very good at this task yet. So here they have this what's it called, this bias from English that the adjective comes first, right? So they say the wrong thing there. Okay, so and what are we doing when we're doing this task? We're doing first of all, we're sort of perceiving these things as like some kind of perceptual whole. So we're kind of binding these things together, the shape and the color. But we're also able to do this kind of perceptual decomposition. So recognizing that shape and color are in fact distinct, even though they're bound together. We can then map these things over here and kind of systematically recombine these in order to get, the mapping goes from this down to the labels, and then we can do this like systematic recombination to get the answer that we got to. Okay, so this is the sort of thing that I mean by systematicity. And here's an outline of the talk. I'm going to talk about, so I'm going to start off talking about a position paper that I recently wrote with some people mostly from Edinburgh, some people from, this guy's from the University of Chemnitz. Sidel and Valentine I met at the Santa Fe Institute, so there's a nice little collaboration come out of that as well. And that's going to be about what systematicity is at this behavioural versus a representational level. I'm then going to talk about some looking at representational systematicity in a vision language setting, and that's very much in the kind of machine learning framework. And then I'm going to talk about some very preliminary results in kind of future directions in letter string analogies based off work with Melanie, and then these are some students who I've been working with on this. Okay, so behavioural versus representational systematicity. So I think hopefully all of us kind of agree that this notion of being able to compose things together and systematically recombine them is important in intelligence generally. So we have this definition from Partee of what compositionality is. So we have for compositionality, this is very linguistically based definition. We have that the meaning of a complex expression is a function of the meanings of its parts and the way in which they are syntactically combined. And we also have from Fodor and Pilishin also write about compositionality and systematicity. And systematicity here is kind of this idea that if we understand the sentence, John loves Mary, then we should also be able to understand the sentence, Mary loves John. And they argue that this is something that's kind of crucial for human intelligence, being able to understand different sentences based out of parts, well, not even different sentences, different concepts that are based on parts of things we've already seen. And they argue that this is done at, that this is crucial at the representational level. And they also assert that, or argue that connectionist systems can't do this. This is Fodor and Pilishin's challenge to connectionism. So Fodor and Pilishin want to argue that really what we need is a kind of symbolic description of how of intelligent systems. Fodor and Pilishin also talk about some other aspects of compositionality. So we have productivity, which is where we can kind of put, we can substitute different parts, or well, productivity and substitutivity means that we can kind of produce longer expressions perhaps than we've already seen. We can substitute parts of some expressions into others and so on. But yeah, really in this, I'm going to be focusing on systematicity. Okay. And we also have, this is Hadley argued that there are 3 levels of systematicity. I'm only going to talk about 2 of them here. So we have weak systematicity and strong systematicity. And in weak systematicity, Hadley argues that the system, whatever system we're looking at, for weak systematicity, the system should be able to generalize to new combinations of relations and arguments where each argument has already been seen in that position. So in this case, we've got ARB and we've got CRD. And if your system can deal properly with these 2 things, then for weak systematicity, it should also be able to deal with ARD. Okay, so we've seen A in the first place of the relation, we've seen D in the second place of the relation, and we can just swap these in and generalize to, to understanding this. For strong systematicity, the system should be able to generalize to new combinations of relations and arguments where arguments can also appear in new places now. So here we've seen ARB and CRD, but we've never seen C in the second position of the relation, and we should, according to strong systematicity, we should be able to generalize to ARC and understand this. When Hadley writes, it's all at the behavioural level now. So we're not talking about compositionality of kind of neural or connectionist representations at all. This is now all behavioural. And now, so generalization here is kind of equated with giving the correct output to some certain problem. Yeah.
So there is some sense in which R has to be symmetric.
Yeah. So in this case, you would have to, you do have to be able to have the objects have to be such that.
That's right. Yeah. The object, because John loves apples.
Yeah.
They're not inferred.
No, you can't. So so this is that's true. So it does depend on.
So that's a restriction on the object, not the.
I mean it's kind of just a general thing. So later on I'm going to talk about some images where we've got left and right. Okay, so there we've got shapes that are in a certain spatial relation to each other. So there it works. And we can probably think of some more sort of general instances where we would want this to happen, you know, without tying it to linguistic aspects. Any more? Okay, and so what do we see in machine learning research? Yeah, so the paper that we wrote about this was really, we called it Behavioural versus Representational Systematicity, an Opinionated Survey. Okay, because in you know, NLP and machine learning, we see many claims of like addressing Fodor and Poloshin's challenge. But we argue in this paper that actually much research in this area involves, well, first of all, building new data sets to test, you know, whether the models can do this, maybe developing new training methods to kind of get the models to be able to do this. But we suspect, we haven't gone into the data sets in full detail, but we suspect most of these only really look at weak or quasi-systematicity. So quasi is kind of in between the two. And most of this work is at the behavioural level. Okay, so the idea is, and you know, Melanie and I's work was like this as well, where we give an input and we see if we get the right output out. And this is what a lot of work does. But we argue that we should care about representational systematicity as well. So why do we care about that? Well, representational systematicity has an impact on the robustness of the system, we would say. So we would argue that if in producing its output that maybe like behaviorally looks systematic, if the actual representations being used are also combining systematically, then that would make the model more robust than otherwise. Okay, you can imagine the behavioural systematicity could appear through shortcuts and so on. So yeah, it's possible for models to develop seemingly correct behaviour that's underpinned by incorrect representations. So there's a really nice example here, they actually have a little kind of web app that you can play around with this on. So these guys train a transformer model to predict the next turn on a data set of taxi rides in NYC. Okay, so we've got basically inputs and outputs. Actually, it's not just the next turn, I think it's a sequence of turns. So we've got like a data set of taxi rides with the origin, the destination, and the set of turns that you have to make to get from one to the other. And they train on this data set, and then they ask their trained model, given a new origin destination pair, you know, now generate me a sequence of turns. And the model does very, very well, like 97% accuracy. However, it turns out that the world model that this transformer has learned is faulty. And this is when they kind of probe to look at what their map of Manhattan actually looks like. It looks like this. Okay, so the black lines are roads that it predicts that are actually roads in a proper map of New York City. And then these red ones are like the additional roads. And so there's lots and lots of these sort of crazy flyovers that the model is somehow is representing, basically. Yes.
How do they access it?
They do kind of probing. Yeah, I can't remember the full details, but we can talk about it afterwards and have a look at the paper. Yeah, they kind of do a sort of probe to look at where the model predicts they can go next, something like this. Yeah. And so you might say, okay, well, you know, why do we care? It's getting really good results on this data set. So why do we care that, you know, underneath it's got this kind of very strange map of Manhattan? And so then they just, you you know, they add in some diversions that the taxi driver has to take while they're on their journey. And then, of course, it just completely breaks down, right? So if like halfway through the journey, they say, okay, this road is closed, then the model sort of does completely different things. So performance is not robust. And, you know, they argue that performance is not robust because it's got this world model underpinning it that is not, you know, not a proper model. Okay, any questions on this? Yeah.
This is the world model.
Yeah, so it's a transformer. So it's basically the same sort of thing as a large language model, but instead of putting in text, they put in like origin sequence of terms that you can make from the origin and destination, and that's what it's trained on. So those are kind of the sentences.
And this is not actual map. Oh, this is.
This is so this is what the model kind of learns to be the map of the thing. Yeah. Okay, any more questions? Okay, so we argue that you know, that we want to attain behavioural and representational systematicity in AI systems. And we want to do this because we want some kind of robust, explainable model. Broad coverage here I've put in because, you know, not a lot of kind of, I don't know, neurosymbolic models and so on maybe don't have like this wide coverage that LLMs do. LLMs have very broad kind of set of data. And so, you know, I've got this nice little glass box with these little cogs inside. There's an analogy to the sort of thing that we want. So how are we going to attain this? So one way that we could attain it is we have a little library of gadgets, and we're going to combine them together in a certain way, and then we're going to get our model. And so this is the sort of thing we're doing when we're building symbolic systems. I call some of the stuff I do compositional, also kind of neurosymbolic methods. It's the sort of thing that we have there. But what's the other thing that we can do? Well, the other thing that we can do is we can kind of train a large language model or whatever, some big deep neural network. And we can hope that these things kind of emerge somewhere. And then how can we kind of find out, well, how can we help them to emerge and how can we find out whether they've emerged? We can use different sorts of training techniques. So we might have meta learning, which I'll talk a very small amount about at the end. Also interpretability techniques where we kind of look inside the model and see, like, can we work out some things that it's actually doing? And what I'm going to talk about is, in the rest of the talk, is I want to talk about some of my work where I've used these kind of more compositional models to try and achieve this sort of thing, versus now some of the stuff that I'm doing where we're looking more at this, trying to work out what these larger models might be doing. Any questions? Okay, so I'm going to move on to talk about representational systematicity in vision language modeling. Okay, so we had this example at the start, and the question that motivated me for this talk, for this bit of research, was whether vision language models, like there's one called CLIP, whether vision language models are able to kind of systematically recombine labels. People also call it compositional generalization or out of distribution generalization. And also whether compositional models can help. So I'll talk about two compositional models that I kind of worked with on this, the particular compositional task that we used in a data set that backed up that task. Okay, so the first compositional model is this kind of type logical approach. This was introduced by, well, so the kind of grammar here was introduced by Lambeck back in 1999, and then Cook, Sargezade, and Clark used kind of category theoretic methods to map between the kind of grammar and vector space models. And so these diagrams here are kind of very similar to the sorts of things that Jules was showing before. So yeah, so how does the grammar work? So the grammar, we have a grammar with type N for noun and S for sentence. And then each type has these kind of left and right inverses. I'm only going to talk about like the left-hand half of each of these, such that if the left inverse of a type X occurs to the left of that type, we can reduce down to 1, which you can think of as the empty type. And if the right inverse of type X occurs to the right of that type, then we can again reduce down to the empty type. We can then build, so we've got these simple types N, S, and their adjoint, the inverses. We can then build complex types by concatenation. And then we can put a string together of these complex types. And then we say, if under these reduction rules, if a string of types reduces to the type S, we judge it to be grammatical. Okay, so it's the grammatically correct declarative sentence. So here we have smelly dog chases kid. So we have an adjective has type N, NL. When you put it to the left of a noun, we can reduce down to noun type. Then we've got this transitive verb here. So transitive verb is chases. And we've got right adjoint of a noun here, left here. And then when those are kind of cancelled out by their arguments, then we just get this S back. So according to this grammar, this is a grammatical sentence. And so, yeah, then what Cook, Sargezade, and Clark did was then to show that we can then map from vector spaces, map from this grammar into vector spaces. And what that allows you to do is construct representations in vector space that you can then plug in on top of these grammatical types. And these grammatical reductions, which previously were kind of purely symbolic, now these grammatical reductions correspond to something in vector space, which is tensor contraction, or you can think of it as matrix multiplication if you want, or extended matrix multiplication. And so here we get the meaning of the sentence by composing the meanings of the words. So this is one compositional model that I've worked with. Another one that I was also interested in was this role filler bindings. Yes.
So maybe this is extremely difficult, but where does the meaning enter? So it seems like you're compiling grammar.
Yes. Yeah. So the meaning. So basically the meanings are in the vector representations up here. Vector and matrix representations. So these are vectors. And you can learn them using various different methods. And I'll talk actually about one specific way we have of learning what would be in these. Yeah. Any more questions? Yeah. Okay. Yeah.
You said grounding.
Meaning is grounding in the world. Yeah, so I have thought a bit about this. And so in if this is just done textually, then the meanings of these individual representations are then grounded by how they occur in text, basically, and that is the grounding, I think. I don't know if it's a very good grounding, but I think I think that's what grounding. So yeah, these these vectors are built based on how they occur with other words in text, and so
Right, so smelly is a coordinate being in a semantic space.
yeah.
It's not a memory of a olfactory sensation.
No, it's definitely it's definitely not linked to olfactory sensations. Yeah, what it's linked to is the fact that dogs can be smelly and kids can be smelly and so on. So yes, in this case it's a map. Yeah, but it's still kind of the grounding still happens in the same way. Yeah. Yeah.
Well, I know vector the matrix.
Yeah, like a thing.
Yes, it's a matrix. It's basically a matrix that takes the word dog. So you can imagine, let's say you've got a vector for dog that somehow represents dog. Yeah, multi-dimensional space. And then this matrix, smelly, converts that particular one into one that's kind of closer to other smelly things. Yeah.
If one is the position the same, that's important. And the position from position related to other words. And the surround word or the context.
Yes.
Context is used, that's important. So dog in relation to smell. If I change it, we completely changes the meaning, but all words are still in there, but the position changes.
Yeah, so if you had like
That's not changes the dog. And that can be a different meaning.
yeah.
So the
And-
position is also.
Yeah, and then you would have this vector would be here and this vector would be here and that would, because this is a map, and the thing you would get out here would be different. Well, you hope it's different.
You must now set off in all the words.
Interesting. Yeah, okay. I'd like to explore that a bit more. Yeah, yes.
Different vectors for the concept of dog, and then we told the objective to just know that the dog is smelly just by looking at the vector representation of the first vector that we get. We could just change the coordinates of the vector to get smelly. We are ready to that it's smelly already without telling it that it's smelly. So it's pointing at the vector.
Yeah, so maybe we could say, let's say, we had a sentence that said like not a sentence, a noun phrase that said the dog that rolled in sheep. Whatever. the dog that rolled in sheep's poo. Right, then we get a vector that describes the dog, and what we hope is that would be more similar to smelly dog than just dog.
But you don't use vector for the word dog.
In this case, yeah, in the way that we would do it here, yeah.
There's only one factor in the vocabulary.
Yeah.
And all the same factor.
So
Yeah.
smelly dog is a vector itself.
Well, in this case, it would be right. So, like, you could have smelly dog would be like you wouldn't learn the vector smelly dog just like as its own vector unless you particularly want to do for some application. The idea is to learn these words and then compose them together so that you. Yeah. So basically, smelly dog is this thing coming out here.
There exists a vector that corresponds uniquely to smelly dog.
I mean, yeah.
Yeah, it's not one of the ones. you
It's
train
not one of
for.
the ones you train on,
Yeah.
but given the matrix
There's
representation
only one
study,
interpretation of it, actually,
yeah.
that is study.
and it's just matrix multiplication. Yeah. Yeah. Okay. Any more? Okay. Okay, so another model that I was interested in as well was this notion of role filler bindings. So, okay, so in the previous one, we're interested in this symbolic representation, this vector-based to distributional representation, and we want to map from one to the other. So role filler bindings kind of has the same, wants to do the same thing. So here we have a symbolic representation. Now here the symbolic representation is as follows. If we have a sentence like dog chases kid, we take, this is a symbol corresponding to dog, and we bind it. So this slash is just a symbol that means bind, and we bind it to this role vector, this role symbol subject, and then we have chases, which is bound to verb, kid, which is bound to object, and then we collect all of these things together in a set, and we say that this set of symbols is a symbolic representation of this sentence. And then from that, we then map into a vector or neural representation where we map each role and filler symbols to vectors. And we map the binding operation to a binding operation, often could be tensor product, for example, outer product. And then this collection operation is then addition. Okay, so we're just adding together this set of bindings. These are kind of generally called vector symbolic architectures. You can have lots of different choices for what parameters can appear in your vectors. They can be real, complex, binary, or limited to 1 and -1 and so on. You have different choices for the binding operation. You have different choices for the collection operation. So there's a whole family of these things. I'm going to just be working with actually holographic reduced representations, which is where you take tensor product in addition, but then the tensor product is kind of collapsed down a little bit to the original vector space. And the benefits of this, we have compositionality. We also have a bit more systematicity, I think, than we do in the previous one, because in this sort of model, as well as a binding operation, you also have an unbinding operation. So it's much easier to kind of, given a sentence representation or representation of a whole, it's much easier to kind of take it apart and recombine. I also liked it because there's kind of biologically realistic neural network modeling, and I've done some work looking at that as well. Okay, so these were the two kind of compositional or neurosymbolic approaches that I was using, and then I wanted to look at this problem in vision language modeling, which is done by this model CLIP. Okay, so CLIP was produced by OpenAI quite a few years ago when they were still open, and this is the kind of this is the evaluation part, right? So basically, what CLIP does, you take an image, put it into an image encoder. The image encoder spits out a vector. So put this image vector here. And then you have a whole bunch of candidate captions. So it could be a plane, a car, a dog, and so on. You might kind of wrap it in something just to make it look a bit better. You put that through a text encoder and you spit out a whole bunch of text vectors. And now what we want is that the vector with the highest cosine similarity to the image vector, it should be the one for the correct caption. So it will spit out a photo of a dog in this case. But this is not really done in a compositional setting. You tend to have you tend to have just a sort of picture of a picture where you sort of have one thing in it, and then we have just single labels for it. So there's no there's nothing compositional that we want to do here. So I wanted to look at how well these models do on compositional tasks. And we had 2 compositional tasks. One where we're just looking at shape and color bindings. And so we give Clip a picture that looks a bit like this. And then we ask which caption is most appropriate. And the possible captions are purple cube, purple cylinder, grey cylinder, and blue cube. And here, purple cylinder is the correct answer, obviously, but we've tried to make it quite difficult by mixing up the shape and the colour. So we've also got purple cube, but we've also got grey cylinder. So the model really has to work to do those things that you guys were doing at the very start of the talk. We also have a second one, which is spatial. And so now we've got cube right of cylinder, cylinder left of cube, cube left of cylinder. That's the correct one, I think, if I've got my left and right. Cube left of cylinder, yeah, and cylinder right of sphere. So again, we're asking the model to disambiguate between these labels, which are very similar to one another. And so we built a data set for this. So as well as those 2 kind of compositional tasks, we just have a single object task, which is easier. And then we do, so then, like I say, with Clip, we kind of give it this image, put it through an image encoder, and we want it to output yellow sphere in this case. Yeah, and so then the question is, so first of all, can Clip do this? And secondly, do these compositional models help with doing this? So for the compositional model, we keep the image encoder the same, and we just snip out the text encoder and put one of the 2 models that I talked about in the text side here. Okay, and so the compositional models are, like I said, we've got this typological model where so a vector for red cube would be the composition of a matrix for red and a vector for cube. A vector for cube behind sphere would be, we would have a kind of tensor for behind, and then cube and sphere would be contracted into that to give you one matrix. And we do a similar thing for the role filler models. In terms of the training, I guess I will skip the details of that. I get how many minutes have I got?
You have, let's say, go for like 10 more minutes.
Yeah, okay. Yeah. So for the training for this, basically, we say we've got, we use a contrastive algorithm. It's basically the same as skipgram, if you know this. So basically, we're getting the vector for the image, the vector for the correct caption, vector for the image, vector for an incorrect caption, and we're trying to move the correct ones together and push the incorrect ones apart. And these phrase vectors are basically these functions that I talked about already. Okay, so in terms of results, it's a bit of an anticlimax because the compositional models didn't do very well. It was really irritating, but also neither did CLIP. Okay, so on the single object, CLIP does very well, and that was expected. On the two object data set, so this top one is CLIP frozen. Okay, so this model has been trained on, you know, a lot of data and images, and basically if you don't give it any fine-tuning at all, it can't do the task at all. It's, you know, it's basically random. Once you fine-tune it, it can do well on the training set, but on the validation and generalization sets, it can't do that at all. So validation and generalization are where I give the model images where the correct labels is a combination of labels that it hasn't seen before. Okay, so it may have been fine-tuned on like yellow sphere and blue cube, but it's never seen blue spheres, and now it has to classify blue spheres. So this compositional generalization. Yeah.
So the model works for one, not for two.
Yeah.
But when I look around,
Yeah.
I look multiple things. I like forget about things around, and I remember one thing, and then I zoom in for the other one.
Yeah.
We just have to like cut it actually. That's true. Like randomly cut it to pieces, and like, do I see something? That's really solve it from single object to two. But for the clean.
Yeah. So I think, yeah. I mean, maybe, yeah. Maybe we could, but maybe that's, you know, kind of, well, we're trying to see if the model can do that by itself.
Yeah.
Yeah.
And just taking the input and randomly cutting it every. Then collecting answers from the cut.
Yeah, so, I don't know. I feel like that's sort of solving the problem that we're asking it to solve. Yeah.
I just feel that from a single object to object in this operation, don't have to care about identifying totally much.
And there's also relational queries, right?
Yeah, there is. Yeah, we'll have to. Yeah. I mean, the point. Yeah.
To the left of the yellow ball to the left of
You can decompose, collect, and put it back. Then figure out where the whole.
Yeah.
Feels to be after.
Still need to be able to compose different.
Yeah, but if you can have, for example, here in the middle, and you get from the single object the ball, you, and then you go back. I'm lucky. I identify things from the picture, and then you go back when you start. Like on the left of this, on the right of this.
You said the teach what left and right.
Here I'm probing. Yeah.
You're building features, which is, what you say is exactly what going in the peer vision did.
Ah, yeah.
And
So why?
so it's just that it doesn't scale. You can't build in every.
That doesn't scale.
No, it doesn't scale. That's why people now, and well, okay.
Yeah. Yeah. So so what do we see? So generalization, basically the system has to deal with new labels that it's never seen before. Like it's seen the components of the labels, but it's never seen them in that combination. And then we have the relational, the relational data set. We found CLIP. We couldn't even fine-tune CLIP to actually be able to solve this problem properly. We could, our typological models, we could do. All of these other numbers that look like they're a bit better than these numbers are not, because they're just purely random. So basically, the question was, can CLIP do this? Can we fine-tune CLIP to do it? And the answer is no, not really. Do the compositional models help? they don't at this point. I'm still, I feel like there are certain things that I could probably do. The representations I used were very big and the data set was quite small. So I think there's probably some kind of compression that could be done here. And, you know, we did get this much better result than CLIP, at least in training. So, okay. And so what are the problems here? Well, we found that like text prompts are not very well distinguished. So if you have, for example, cube left sphere and sphere left cube, those are closer to each other than sphere right cube than it is to sphere right cube. So basically on the text side, the text prompts are not well distinguished. And the image embeddings do better. So we do get this separation of things that we want to be separated. But in some cases, but then also in others, they're a bit more mixed up. We also compared to a different sort of classifier as well. I think I'll just skip over that. Okay, so just moving on to analogies. So I did this work with Melanie last year, and we saw that GPT models don't solve analogies robustly. So some questions I'm exploring with my students at the moment are whether we can use other training methods to train a system to actually solve them more robustly using meta learning, and what kinds of representations might LLMs be using in solving these problems. So far we've looked at function vectors. Now all the results here are extremely preliminary, and so, you know, if you see me give a talk in 3 months' time, they may be completely different, but there we go. Okay, so I'll just skip over letter string analogy. So actually at the break, someone was asking me, you know, there's no correct answers to these things, and Melanie said that as well. So for example, here, if ABCD goes to ABCE, what does IJKL go to? And most people will say IJKM. But you could also say IJKE, right? The rule is replace the last letter by E. And it's not very satisfactory, but it's, you know, that's what there is. We had all these different task types. And yeah, I'll come back to those, I think. So what we wanted to look at was whether we could get the model to learn a bit more robustly using this technique called meta learning. So meta learning, you've got these sort of mini little data sets, and the model has to learn based on these little mini data sets. And then at test time, you have a new data set that it hasn't seen before, maybe, and see what it does in that case. And very nice paper came out by Brendan Lake and Marco Bruni in 2023, where they showed that you can get human-like systematic generalization through meta learning. So this is all from their paper. So basically, humans and the transformer-based model get these inputs. They don't get these headings. Okay? So they don't know that, you know, this is a description of a function and this is like function composition and so on. They just get these sort of input-output pairs. So this is what they get. I mean, you can have a look and see if you can work out what the functions are. And then they put it into this transformer-based network and get the transformer to output. And they get very, very nice results on this, which, you know, they get superhuman performance, like once they've trained long enough, and they say that that the model can do this on kind of new rules and so on and so forth. So by new rules, I mean we have. So here's. Okay, so this function says, okay, take lug. So lug is this one, and triple it. So fep means triple, basically. And what they say is that their model can now do this, and like if you come up with a new rule, then the model can deal with a new rule.
It's a good path to superhuman performance, to make it very hard for humans.
No, humans can do like 80% actually. Yeah, human performance is 80%, which is fine, I think. Okay, so with the master's student, we're basically just taking this model and we're giving it letter string analogies. Was that a question or?
Yeah, you go backwards, like
Yeah.
I was trying to read it. And then if you have the first function component, you have to read that PQ. But if you say that it doubles it, shouldn't it the green block be doubled the next table?
Yeah.
PQ.
What?
Under function composition.
Oh, here, yeah.
That PQ.
Yeah, I guess it depends on yeah.
Like 3 greens and 1 blue then?
Log fat means like triple fat, triple lug, right? And then kiki with, yeah, I guess means like put it next to, concatenate with, yeah. I mean, that's one of the things, I mean, that's one of the things you have to work out, I guess, when you're doing this. Yeah, that's part of the, yeah. And you don't get told that you're doing a function composition as well. So, but yeah, humans, I can't remember how they actually, humans was like 80%, but I can't remember how they recruited the humans, whether they were you know, students in like sitting it in real life or. Okay, yeah. Okay, so yeah, so now we're doing this basically with analogies. Okay, so the idea is we do that, we give it the query is something like IJK. We have a study example, that's the terminology that they use, which is ABC goes to ABD. And yeah, this symbol goes to is like a kind of dedicated symbol that is kind of trained, you know, in the training. And then we give it an alphabet. And yeah, and then the model has to do the same thing. At the moment, we're training on 10 different rules over multiple alphabets. So we're taking like an alphabet, we're taking the standard alphabet, mixing it all up. But this notion of, I think this notion of, you know, how commuted the alphabet is doesn't really like correspond here to how it did in the previous one. So we're just using multiple alphabets as a way of having a bit more data, I guess. And then we're looking at generalization. So for generalization, we're looking at having these same 10 rules, but just maybe over different alphabets and different portions of the alphabets. We want to look at combinations of C rules, and then we want to look at completely novel rules as well. So yeah, initial results so far are that, so we have, you know, the student that has not been working on it for that long, we haven't got to all of the generalization yet, but so far, something kind of interesting is that these successor and predecessor patterns, we can't learn these together. So yeah, I should have reordered this side. So successor is this one example that we've been talking about kind of the whole time. And then predecessor is where you have like BCDE goes to ACDE. So it's like decrement the first letter. And yeah, and basically what we've found is that we can't learn successor and predecessor together, and they also kind of really interfere with each other, right? So we get one, you know, one goes up, the other goes down, and so on and so forth.
What do you mean by learn them together?
I mean, if we do like a set of tasks where successor and predecessor are both in the same like training set.
If we hold one out, then it's.
Yeah, if we hold one out, then yeah, they can. So this is predecessor, but we can also learn successor as well. We just can't, so far we can't learn both of them together. So there's like this thing going between them. Okay, and then yeah, this is really as far as we've got, but we're kind of pushing on with that, and I'd love to talk to people if people have knowledge in this area and would like to kind of discuss. Okay, and then we're also with another master's student who's at the back now, looking at mechanisms behind analogy completion in LLMs. So we find performance, so performance depends on the task, right? So this is similar to this is a kind of breakdown of the graph that Melanie showed earlier. And we want to do some kind of mechanistic interpretability techniques. For mechanistic interpretability, you always have to have a task that the model can actually do. Otherwise, there's nothing to interpret. So all we're going to look at is this one here, where it's successor on just a normal alphabet. And at the moment, what we're looking at is function vectors. So function vectors are basically a set of heads with a causal effect. So that's not what function vectors are. So there are a set of attention heads which have a causal effect on in-context learning. Okay, so if we give a model a kind of in-context learning prompt, so we have arrive goes to depart, small goes to big, common goes to it can do rare. Okay, so we make sure it can do that. And then we go, okay, the word fast, then we give it this prompt, zero-shot prompt, the word fast means, and then we add in, we derive this function vector somehow, we add in the function vector here, and it will say slow, because we've basically, because that's what we've kind of trained it on in this in-context learning. And the way that they do this is they identify a set of heads that have a causal effect on in-context learning generally, and then the function vector itself for a specific task is computed by just giving a whole load of ICL examples, and then adding in the and then taking the vector that corresponds to that ICL task. So it's very exploratory at the moment, but one question was, we wondered, does a next item function vector help with successor tasks? So they have a bunch of next item ICL prompts, like Monday goes to Tuesday, so on and so forth. 1 goes to 2, 2 goes to 3, and so on and so forth. They also have all the alphabet, which is quite helpful in this task, you'd think. With explicit prompting, the models can get up to around 80%. So these are open source models. They're not as good as the GPT models that we looked at before. Gets up to about 80%. We then look at baseline with where we literally just give it a prompt and see if it gets the right answer by chance, and it doesn't. And then we try giving it the next item function vector as well, and we get, it doesn't work for that. Okay, fine, But also, neither does this success. If we try and give it a successor function vector, that doesn't work either, right? So if we try and generate a successor function vector based on a whole bunch of successor problems, this is also 0%. So it feels like, these people have kind of identified these mechanisms, these function vector mechanisms, but they might be very specific actually to the task that the tasks that they've been derived from, and are not, don't actually work for other tasks. So this is a shame, but we can, I don't know. Again, if you're interested in this and would like to chat more or have some ideas, then I would love to talk and see what we can do. Okay, so just a summary of the talk as a whole. So I talked about systematicity and why we want systematic behaviour to be underpinned by these systematic representations. I gave this case study in Vision, and then I also talked about analogical reasoning and attaining systematicity through meta-learning and interrogating internal representation. So thank you very much. Please feel free to get in touch, and a lot of this work was done with a whole bunch of collaborators, so thanks to them as well. Okay, thank you.
We have time for a few questions.
Yeah.
I have a question, but I think also about the example that your data set.
Yeah.
I was thinking that maybe it's a bit unfair because I have the feeling that it's impossible to really certain map from your data set. So that you also not be able to do it. And then do you think there is any kind of fundamental thing in current machine learning structures that they can kind of do these things that this that, or do you think maybe it's also a problem with we just don't have enough data?
Yeah, I mean, potentially it could be that there's not enough data, but there is also this thing that it's kind of made up all this extra stuff, right? Whereas I think with a human, they maybe wouldn't make up those extra kind of loops.
I feel like I have that. Though.
Oh, okay.
If I think about my world model of the city, then weird places are sort of connected because I cycle the route a lot.
Yeah.
And I have all these
Yeah.
non-geometric.
Yeah. Yeah. Yeah.
So the last part of the book, so we said now the function factors may not work because they are trained. They're not generalizing things, but if you train these function factors specifically for this task, then it should work.
No, so the way that the function vectors work is that these they take a set of tasks, a set of in-context learning tasks, and they find which attention heads are causally effective overall on those tasks. And then they generate a specific function vector for each task by then running in-context learning and getting the output of those heads. So whereas they were claiming that these heads are kind of general in-context learning heads, and I think possibly these are not really general in-context learning heads, they're just in-context learning heads that happen to be causally effective for this suite of about, I think they've got 10 or 20 in-context learning tasks that they want to do. How many is it? 30. 10. Okay, 10. Yeah. So they've got 10 tasks. So this task is opposites. This task is translate to Spanish. They've got a next item and a previous item task. So they've got these 10 tasks. And their claim is that these heads are, general and context learning heads, but perhaps they're not. So, this is called is from David Bauer's lab. I think it's called something like function vectors. I can't remember. I'll send you the link. Yeah. But also I thought I had a slide on it. Claire and her student have a very nice paper on concept vectors. Yeah. Which I think could be a good way of using this. Yeah.
I have a bit of a naive question. Because I think it's a sort of maybe it's a very deep linguistic truth. But why do nouns get to be vectors and the rest have to be vectors? Right.
Yeah, I mean that's true. You could,
But there's a
it's a transformation from a matrix to a vector. Yeah. Well, that comes out of the grammar that we use, right? And the grammar that we use has a single atomic type for noun and a single atomic type for sentence, and then the other ones are combined. And I did ask somebody who works in this area why we would do it. Like, why wouldn't we just have verbs being the sort of atomic thing? And their answer was, well, try and write a grammar like that.
Okay.
And see if it works.
Right.
So not very satisfactory. But you can, but sometimes you don't have nouns being being vectors. Does anyone work in this kind of area at all? Okay, so when you work in this area, so normally you would actually write this out as not normally, in other kind of formalisms, you would write this out looking a lot more like a logical proof, right? And when you write it out as a logical proof, I think for various reasons, it's nice to have all the sort of reductions happening on one side, because then it makes a tree that is more well behaved. Jules, do you have a? No, that's fine. If you're writing out a logical proof, is there you want the sort of proof tree to be sort of well behaved and only branch in one direction? Is this true, or maybe yeah? Anyway, so
That would be looking for that more proving thing.
yeah, so you want that to happen, and so what you do then on this side is you use something called type raising, where you say, okay, well, I'm now I've got my noun, let's say the presence of the verb, and instead of the noun now being a single point, an atomic type, I'm now going to make it be a type that takes verb and returns back a sentence. So you can do this type raising thing. And some people equate this type raising to affordances, which is, I think, interesting, because that's the sort of as that you were talking about, like when you say paper and a book as paper, or paper as a book, that as is affordance, this notion of affordance, and this particular researcher views this kind of affordances as being represented by type raising. I need to work out exactly how that works. I don't know quite yet, but yeah, yes.
We also express the German material way that we have more flexibility.
Flexibility in what sense?
So yeah, I'm not sure if you will explain that you have linear information.
Yeah.
When you look at the words like verbs and adjectives or verbs, and you would get these just one notch higher. We don't have a transition. The opening is the higher level. I think that's the question. Which is the relationship with more than one object. Yeah, when you get this or
yeah,
the verbs are
these will be, yeah.
The verb has two legs.
Yeah, so each leg is like a tensor order, tensor dimension, tensor index. Thank you. Yeah, so a noun is a one index tensor, adjective is a two index tensor, a transitive verb is a tensor with three indices, and you can have more if you have a ditransitive verb, which is where you have like John gave the ball to Mary. Then gave is something that needs four legs. Yeah.
So I propose we do further questions over drinks in the restaurant. And thank Martha again.
Cool, thank you.
So thank you very much for attending today. This was really great. As intelligence is absolutely a suitcase word. I didn't expect to come up with sort of the one definition of intelligence, but I think looking at it through analogy and abstraction, these helped me a lot.